Okay. Zoom out. Okay, so we said that this last time we said that we have this angle, and the initial side of the angle is going to be pointing at the 3 o'clock position as if on a clock. Okay, so that's our initial angle. That's not coming up. Okay, so the initial angle, the initial side of the angle is this ray right here pointing at the 3 o'clock position. And then what we'll be doing for the next month, we'll be sweeping an angle counterclockwise from the 3 o'clock position. So that's talking about the terminal side. So we think about sweeping an angle counterclockwise from the 3 o'clock position. Okay? And we're talking about now measuring the openness of that angle. Measuring the openness of that angle. So we started. Okay. So we looked at that small circle and we threw a radius on there. And so I'm putting a purple radius right there on that. And what did? We took that radius, we maintained its length, and we peeled it from its spot and we wrapped it on the circle. Okay, and that defined some angle that cuts off that ray, right? So or that arc. So here's this angle that I'm showing that cuts off an arc length of what? 1 radius. Okay. And so what about if I chose a different circle? And I did the same thing. If I took that radius and laid it on its circle, how would it compare to this first angle that we drew? A bigger arc? But how will it compare to the angle?
It's the same.
Yeah, so taking a different circle and taking its radius and laying it on its circle will have the same, right, it will have the same angle will cut off that same arc. So if we're talking about how angles are a fraction of the circumference, then how about using radius length to mark off arc lengths? Does it work? Because no matter what circle we choose, the same fraction of the circumference is preserved, no matter what radius we choose. So those are all a length of 1 radius length. And that's how we define the numerical measure of a radian. If it's 1 radius length, that's cut off by the rays, then the angle measure is. Can you take off the headphones? Thank you. So if it's 1 radius length, cut off by the rays, then what angle is that in radians?
1 radian.
He wants 1 radian. Agree with that? That's how we define radians. The number of radius lengths cut off by the rays. So the slight difference is that radians are measuring the openness, the angle measure. Radius lengths are measuring the arc length. So it's a subtle difference, okay? So radians are about how open the rays are. Radius lengths are arc length. But the number is the same. The number is the same, and that defines radians. Okay? We define radians by number of radius lengths cut off by the rays. Okay? So here I've got an angle that cuts off 2.4 radius lengths. This angle cuts off 2.4 radius lengths. in any circle, right? It's all 2.4 radius lengths. What's the angle measure? Morgan. The angle that I'm showing here cuts off 2.4 radius lengths no matter what circle you look at. So what's the angle measure in radians? 2.4 radians, right? 2.4. Somebody gets it. Okay? So here is an angle that cuts off 3.3 radius lengths. Whether it's the purple, blue, or red, or any circle with center at the vertex. What's the angle measure in radians? Malin? 3.3 radians, right? That's how we define radians, as the number of radius lengths cut off by the rays of the circle. Okay, so we'll just zoom in and look at this. We'll just focus on this one circle that has radius 1. But actually, we can think of this circle with radius 1 as any circle in the universe, okay? It's called the unit circle. This is called the unit circle. But it's not one special circle. It's actually all circles. How can we think of... Okay, so suppose this circle has radius of 14.8 meters. Okay, that's a fairly big circle. Probably would not, no, it will not fit in this room. The circle would not fit in this room, right? It'd be, it'd be pretty big, okay? But how can this, the unit circle, which has radius of 1, how can it be thought to represent this circle, radius 14.8 meters? Anybody have an idea? So this circle, the unit circle, could still represent this circle that has radius 14.8 meters. How could it do that? Yeah. Okay, proportional. But how is it that this circle, who has a radius of 1, this is 1, this is negative 1 over here, they're proportional, that's true. But how can it truly be seen as the circle with radius 14.8 that would go out into the sidewalk and on behind the classroom, be a big circle? Yeah.
They would have the same angle in degrees. That would be similar.
Okay. Angles would all match up. They'd be proportional. Any other ideas? Yeah.
You could just simply multiply the radius by 14.8, or any radius for that matter.
Okay.
To give the new radius, because 1 times any number will be equal to that. And since the angles are all going to be the same for 1 radian, the angle measures will be the same.
Okay. Good. All right. So lots of good ideas there. So let's just get down to brass tacks. What does that 1 mean? If the circle is truly 14.8 meters in radius, what would the 1 represent? No, but it's still 1. 1 what? 1 radius length, right? So this would be 1 radius length, and we know that our radius length is?
1 radius.
No. It's not an angle. There's no angles here. I'm just talking about the radius. So 1 just would be standing for 1 radius length, and we would know that our radius length is 14.8 meters. Okay, so what would this right here, this is 0.5. In our circle of 14.8 meters, what would the 0.5 represent? Oh, not meters, sorry. The 0.5 would mean what? 1/2 of our radius. So it'd be half of 14.8 meters. So in this way, in the unit circle, thinking of the 1 as not 1 like distance unit, but 1 radius length unit, it becomes every circle. Whether it's 0.7 centimeters in radius, 1,000 miles in radius, 100 light years in radius, the 1 would mean however long, 1 radius length. And 0.5 would mean half of the radius. And 0.9 would be 9/10 of the radius. Okay, so the unit circle isn't a particular circle. We want to think of it as every circle. It's every circle. Okay? That 1 then stands for the length of a radius, 1 radius. Okay. So what I want you to do is, I want you to, by estimation, so notice here, so we can sweep out all the whole number, and you had practice with this. So that's 1 radius length, therefore 1 radian, then 2, 3, 4, 5, 6, and then full rotation. So I've marked off the whole number of radius lengths starting at the 3 o'clock position and going counterclockwise. Okay? So based on those, so in your notes, by estimation, I want you to sketch the angle swept counterclockwise from the 3 o'clock position that has these measures. 2.5, 0.4, 3.8, 6.1, -1, and -5. So some practice, okay? So you're sketching by estimation these angles swept counterclockwise from the 3 o'clock position. And I'll take attendance. Okay, how did 2.5 go? Justin, can you describe to me where the terminal side would be for 2.5 radians? Oh, so here, when we have these angles swept counterclockwise from 3 o'clock, we name the quadrants. This is the first quadrant because this is where our first angles are. And then quadrant 2, quadrant 3, quadrant 4. So that might help. So the terminal side for a 2.5 radian angle. Second quadrant. Toward the top here, toward the middle, or toward the bottom? And what's toward the middle? Let's see. 2.5. There's 2.5. So, and what does the 2.5 stand for? Justin, so can you just describe what does 2.5 mean?
It's the degree of radians for that in radians for that angle.
Right?
In the second quadrant.
And where does that number come from then, as 2.5 radians?
Is it because I'm actually not quite sure.
All right, I'll get you started. It's because the rays of the angle do what? The rays of the angle do what? Taz? Subtend. Right. Yeah. It's because the rays of the angle subtend or cut off 2.5 radius lengths. 2.5 radius lengths. Okay, Anna, how about 0.4 radians? Can you tell me? First quadrant. Toward the top, toward the middle, or more toward the bottom? You said toward the bottom? Yep, I would agree. That's 0.4 radians. Because? The rays?
The rays
Subtend?
subtend the 0.4 radius.
That's right. Exactly. 40% of a radius, or 0.4 of a radius, is subtended by the rays. Okay, 3.8. Walter, did you get 3.8? Quadrant 3? And where? Toward the top, or in the middle, or at the bottom? Toward the middle. I'll show you 3.8. There it is. That's 3.8 right there. Okay, what about 6.1? Jared, R. 6.1, yeah. So which quadrant, and about where will the terminal side be? 6.1? 6.1 radians? Quadrant 4. And towards the bottom, the middle, or up here? Top. So here's the whole circle. So here's 6. Yeah. So 6.1, that's the closest I can get. So that's 6.1, a little bit more than 6. Radius lengths cut off by the rays. Now what about negative? So Nadine, or Huda. Right, you're going to go clockwise. So how do we know how far to go clockwise? A little bit louder, what's that? I couldn't hear you. So tell me where to stop. Something like that? Right, so now the green arc. What's significant about the green arc then? Can you tell me about the green arc? What is that? How long is that green arc? One radius length, right? It's going to be one radius length, but now clockwise. One radius length clockwise will be an angle of -1 radians. Okay, so what about -5? Christian, did you get -5?
I did. It's going to be in quadrant 1.
Quadrant 1.
About towards the middle. Maybe more towards the top.
So if this was, coming around counterclockwise, if this is 5, how can we use that to help us? Now we're going to go this way, we can go 5 this way. So where would it be? Straight up from this, right?
Yeah.
So yes, it'd be like here. It'd be the same distance, 5 radius lengths going clockwise around, that we went counterclockwise before to get 5. So now it's the green, again, it's the green, it would be the green arc. So close I can get. Yeah, that's the closest I can get right there. So the green arc would be our -5 radians. Okay, any questions on those examples? So what's the disadvantage to these whole numbers of radians? What's kind of problematic about having these whole numbers? 1, 2, 3, 4, 5. Alex?
Well, you end up having 6 whole ones, but then you still have a chunk at the end before
Right.
leaving a full.
Right, so in the background of what you're saying is it'd be nice to have one full rotation, or half, right? Because this is a nice symmetric place. So these don't land on nice places on the circle in terms of symmetry of the circle. Top, bottom, left, right, okay? So I think at the end we talked about halfway around the circle, right? So this is 3. That's 3-ish. And that's 4. So I'm showing 4 right now. And 3 is this one here. So halfway around is between 3 and 4. Closer to 3 or closer to 4? Closer to 3. And in fact, you're familiar with this number, but you might have not known before what it meant. So what is it? Pi, okay. So if we went 3.14 radius lengths, would we be halfway around? 3.14. Would we make it halfway around? Close enough. So would we precisely make it halfway around? Would we fall short or go too far? We'd fall short, okay? What about now? Would we make it? Fall short or behind? Or over? Still fall short. Okay? So we know that there's lots and lots, in fact an infinite number of, is it 6 after that? 2? I don't remember after this. But even 3.14159 will still fall short. Even though it's a very tiny bit short, it'll still fall short. And for every time we add a decimal place, pi has an infinite number, we'll get closer, but we'll still never get there. Okay? But there is this number, okay? It's an irrational number, an infinite number of decimal places. There is this number that is precisely let's see here. N equals okay, there's this number pi that is precisely what? So explain to your neighbor what the number pi means. Okay, so it's 3.14159, infinite decimal, yes, it's all those things. But what's the meaning of it? Say it well to the person next to you. What's the meaning of it? Do you have a question? It's not repeating. It's non-repeating.
So it just
An irrational number. Right? So it never has a repeating pattern. If you said 2 or 3 words, it's not enough. It doesn't do the job. Okay? So you need kind of there's some meat behind it. It's not just blah. So if you said half a circle, that's not right. What about half a circle? What about half a circle is pi? Okay, let's see how we did. How about Jared S? Can you give me a good definition of pi? Stop right there. I like that start. The number of radius lengths. If you started like that, you've done good. All right, keep going. Number of radius lengths. That cover exactly half of the circumference. Right. Pi is a number. It's counting radius lengths, right? It's a number of radians. It's counting radius lengths. Like he said, to get exactly a half circle. To get exactly a half circle of arc length. Okay? So that's well done. Okay, so from pi then, we can get, do blue. Yeah. We can get lots of nice places, convenient places on the circle. So pi we know is exactly halfway. I'll do red. Okay, so what's a quarter way, or 1/4 of the circle would be? Half of that, right? Half of a half circle. Okay, and then what about 1/8 of a circle? 1/8 of a circle would be like kind of halfway up the first quadrant. Pi over 4, half of that. Okay, and then if we wanted to say we wanted to go 3/4 of the way around the circle, so we do a half, a circle, and then we do another half of that. Okay, I heard 3 pi over 2 and 4 pi over 3. So it's pi plus how much of pi? To get 3/4 of the way around the circle here, we do pi, and then how much more? Another half a pi, right? So it'd be pi and a half. So you could do 1.5 pi would be the bottom of the circle. Or 3/2 pi. But the point is, it's half the circle pi plus half of that, 1.5 pi. Okay? All the way around the circle. 2 pi. So is 2 pi 6.28? That's just an approximation, okay? So precisely, it's 2 pi. 6.28 is just a rough approximation.
Is there also an infinite
Oh yeah, it's 2 times, well, it's not an infinite number, it has an infinite number of decimal places. Yeah, it has an infinite number of decimal places, right? Because you're going to take all those, you're going to take the whole thing multiplied by 2. Okay, up here would be, what, 3/4 of pi? 3 pi over 4, or 3/4 pi. And then this would be, so now we're just going by quarters now. So 1/4 more than pi would be 5/4 pi. And then 7/4. So what are those? That's 8 nice places on the circle. We keep splitting in half, right? We keep splitting everything in half. But here's the thing. So I think lots of students, what happens is we start dealing with these locations on the circle, and what this turns into is just like kind of the label for that place. Like it's just like a name. Like the name of this place in the circle is 3/4 pi. And the name of this place is pi over 4. Okay? But you can't forget that these are truly numbers. So don't go to your calculator. This number right here, that is a number. It's a value. Okay? Based on your understanding of what we're doing, can you estimate what that value is without your calculator? Don't use your calculator. Can you make an estimate for what that value is? For instance, 10.4, negative 3.6. Okay? That's the kind of thing I'm asking for. So based on your understanding, can you come up with an estimate of what that number 5 over 5/4 pi is?
So I need 5 over 4 times pi to get that number.
Right, and I'm not asking you to do a mental computation. I'm asking you to think about the meaning of this number, and based on our meanings of what we're doing, make an estimate at what that value is. So, Brian, you want to give it a try? What are we doing here? Hamid,
3.7.
what'd you say?
3.7.
He wants 3.7. Why 3.7?
Because it's close to 4.
Close to 4.
Yeah.
So we're still, even though we're doing all these things with pi, we're still counting a number of radius lengths, right? And what was this one here?
4.
That was 4 radius lengths from the 3 o'clock position. So he's looking, saying, oh, it's a little bit shy of that. So 3.7, maybe a little bit more than that. But 3.8 maybe. All right, so our guess is 3.8 because it's shy of 4. Radius lengths swept from the 3 o'clock position. Now put in your calculator. Put 5 pi over 4 in your calculator. Let's see. Uh, 3.93. Okay, so that's pretty good estimation. And so a better approximation then would be the number of radius lengths swept counterclockwise from the 3 o'clock position. Okay, so let's say one more time. Pi over 2. So pi over 2, just a quick estimation of what pi over 2 would be. Jonathan, what value is pi over 2? No calculator. We're counting radius lengths, right? And we know these.
1.6.
He wants 1.6. How many radius lengths is that right there? 1. How many is that? 2. So pi over 2 is about 1.6, and it's actually 1.57. But 1.6, that's a good estimate. Just eyeballing it, okay? Okay, so you're gonna use these values a lot, okay? Remember that they're values. They're not just labels for points on the circle. They're actual numbers, and they're still counting how many radians or how many radius lengths you're sweeping from the 3 o'clock position. It's really important, okay? All right, so let's talk about, we're back here at 1 radian. So we said that it's all about fraction of the circle. So what fraction of the circumference is cut off by 1 radius length, or by 1 radian? Figure it out. What fraction of the circumference is subtended by an angle measuring 1 radian? Everyone do it. You should be able to do this. I'll show it to you. There it is. What fraction of the circumference is that? Cut off. The angle, so that rays cut off an arc length. That's subtend. The rays subtend an arc length. So what fraction of the circumference is subtended by an angle measuring 1 radian? Khan, did you get it? Okay, let's get it exactly. How about, can we do it precisely? 1 over 2 pi. Right, so it's 1. So if 2 pi is the full rotation in radius lengths, then we're taking 1 of those, and that's the fraction. So let's get an approximation. 0 point, I think it's 1.5, what? 915? Is that right? Okay, so explain the meaning of that number to the person next to you. What does 0.15915, what's the meaning of that number that we just found? Go, what does that mean? So what's the significance of 0.15915? Nadine, do you know?
It represents like 6 in the circle, so it's 1 radius.
It's 1 right. Is it a sixth of the circle? A little bit. Is this 1/6 of the circle? Is that right? I think 1/6 is 0.167. Yeah, okay, so it's saying that it represents a little bit less than 1/6 of the circle. Or what percent of the circle is it? What percent of the circle does the angle cut off? Yeah.
About 16.
About 16, 15.9%, 915%. Yeah, so it's the fraction of the circle, or the percent of the circle, cut off by an angle that has a measure of 1 radius length, 1 radian. Okay, so this provides us a really slick way of converting. Okay, so conversions. We don't have to memorize any formulas if we just understand percent of the circle, and we know in any given in any given unit what a full circle is represented by. Okay, so let's say here I've got we say we've got 212 degrees. So first of all, let's estimate where would you estimate approximately where the terminal side would be, okay? So everyone think to yourself, where should I put the terminal side of this angle to represent 212 degrees? Patrick, can you tell me? Okay, so can you be a little more specific? Where in the third quadrant?
Because
Or top, middle, or bottom?
towards the, let's say, middle, well, actually, towards the bottom. Middle, because it's, if that's 180 degrees.
180, okay.
And the 3/4 is 270 degrees.
Okay.
Then it would be closer to that side than the other side. Closer to the 3/4 side.
How far away is 212 from 180?
Oh, sorry, no, closer to the other side.
Yeah, so it'd be like this, right?
Yeah.
That's about 212 degrees. Okay, so how can we, without trying to use or memorize a formula, remember a formula, how can we use percent of the circle then to get the equivalent number of radians? Alex?
Figure out the percentage of 212 is equal to the total circumference of the circle in degrees 360, so you put 12 over 360.
Okay, so you're saying the percent, the fraction of the circle that's the same as 212 degrees is what again?
212 over 360.
212 over 360. And let's just get a rough approximation of that. Was it? 0.58?
Continuing
Lots of eights, okay. So, and does that, looking at the picture, does that make sense? 0.58, does it make sense looking at the picture? Tim, does it, 0.588, looking at that picture, does that make sense?
Yeah.
Why?
It's more than 50% of the circle, but it's not that far.
Yeah, so it's like, we're saying like 8% or 9% further than halfway. Yeah, so that looks like that's about right. And so now, how can we use that fraction of the circle then to find how many equivalent radians it is? Alex, keep going.
Well, then you would multiply that ratio that you got
Uh-huh.
by the total amount of radians that are around the circle, which is 2 pi.
And why? So why would that do that? What would that accomplish? Why do you want to do that?
That would give you, let's say, you're pretty much going to take that percentage that you have
Uh-huh.
in degrees, and the only thing you're going to do is set it up in measurements of radius things.
Okay. Yeah. So we got this fraction of a whole circle, and if it's radians, then we want it to be that fraction of what? We want radians. But so to get the number of radians, it's going to be that fraction of what value?
the whole circle in radians.
2
2 pi.
pi. So we're going to take that fraction, that 0.58888, right? That 0.588 of 2 pi, or multiply by 2 pi, will get us how many radians is the equivalent angle. All right, make a guess. Before you calculate it, make a guess about how many radians do you think that would be? Ahmed? 3.5 or something like that, right? In between 3 and 4. And what do you get? 3.27?
3.7.
Nice and loud.
3.7.
3.7. 3.7 radians. Okay, so you see, you don't have to, all you have to know is that there's how many radians in a full circle? 2 pi, and there's 360 degrees. Or so gradients is another way of measuring circles, and with gradients, so before I go on to that, how about any questions on this example? So we took the 212, we used it to get the fraction of the circle that 212 degrees is, and we took that fraction of 2 pi. Yeah?
If I try to divide by 360 and then multiply it by 212, will I give the same answer?
Yes. So why are you asking that? Is it something you've done in the past?
Yeah.
Right, so it's just a formula, right? So yes, it'll work, but if you forget that, then you'll have nothing to fall back on. So what I'm really encouraging you to do is use kind of your understanding of this. With 212, we can get that percent of the circle. And then we take that percent of 2 pi. And then you never have to remember a formula. You see? I think that's better. Yeah.
By using the percentage.
Always start by finding the percent of the circle or the fraction of the circle. And then it'll take you to any other unit of measurement that you want. Okay, so a gradient, one gradient, or an angle measuring one gradient cuts off 1/400th of the circumference. Okay, so an angle measuring one gradient cuts off 1/400th of the circumference. So let's start with, how about 92 gradients. So first of all, where do you think, can you estimate 92 gradients? Can you estimate where that terminal side of the angle will land? Or how open is that angle? 92 gradients. And then find, so 92 grad is grad is the nickname for gradients. So 92 gradients. First, estimate the openness. Estimate where that terminal side is going to fall, and then find the equivalent number of radians and degrees for 92 gradients. Okay? So given 92 gradients, find the equivalent number of degrees and radians. Go, work together if you need to. First, estimate what the angle, where you think it'll land, the terminal side.
Where do gradients come from? What are they used for?
It's just another system. So I don't know where they originated. But like degrees, it's just another system that just isn't as popular as degrees.
It is 400, right?
1/400, yes. So an angle measuring one gradient cuts off 1/400th of the circumference. An angle measuring one gradient cuts 1/400th of the circumference. Okay, so let's estimate first. Diana, where do you think, how much openness is 92 gradients? Like, where should I put the terminal side? First quadrant. Can you be more specific? Towards the top. And why, like this? Even more? Like that? Why do you think there? So what led you to make that guess?
Well, I'm looking at the 92
Uh-huh.
and then they give me 0.23.
Okay. So you get the percent to do that. And why did 0.23 suggest that you should be there?
Because each quadrant would be 25%.
Good. Yeah, so it's a little bit shy. 23% would be a little bit shy of the first quarter of the circle, 0.25. All right, so for the percent of the circle, you said you did 92 over 400? Is that right? Keep going. So how about, what did you do first? Did you do degrees first or radians? Radians. So how would you calculate how many radians is 92 gradients? Okay, so you took that fraction, 92 over 400, and you said you multiplied it by? That's it. So we take that same fraction of 2 pi. And estimation. 4.4? 1.45. Which seems about right. We know what one radian is about here, and so it's almost 1.5 radians. Okay, somebody else. How can we get number of degrees? Omar.
You multiply the number of radians by 360 divided by 2 pi.
Okay. And how'd you come up with that? Is that something you remember from before?
With the homework.
Yeah. So can we use percent of the circle to do it? Can you use percent of the circle to get degrees?
Yeah, I guess so.
I would, yeah, that's what I'm encouraging you to do.
I haven't actually figured that out yet.
How do you, so what percent of the circle are we at?
33.
92 over 400. How do you take that percent of what? Do we need to,
360.
yeah. How do you do it?
Yeah, I mean that number,
Mhm.
0.23 times
Right.
360.
That's it. That fraction of 360. You're going to take that percent of 360. And it should be, what, a little bit less than 90, right? What'd you get? 82.8? Okay, questions on conversions. So practice this. You know, if you're involved in some complicated problem down the road in your engineering endeavors, and you forget this little formula, you know, it won't serve you if you don't remember a formula. So, but understanding and using percent of the circle will serve you, and you can always fall back on that. Yeah.
So we come up with our own unit.
Yes, you can.
So like, when we say that a circle has 12 arcs in it,
12 what?
arcs,
12 arcs?
arcs.
Marks.
Yeah.
Oh, like me? I suppose. Okay. So how many marks is 5 radians? Go. How many marks is 5 radians? You can all thank Alex. How many marks is 5 radians? Where's 5? What quadrant is 5 radians in? 1, 2, 3, or 4? Quadrant 4, kind of towards the bottom. That's about 5 right there. Okay? And so, how are we going to get, what are we going to do first? This, Jared. Did you get it?
Yeah. I took 5 and I put it over 2 pi.
Right? Which would mean what? What would that number mean?
That's the percentage.
Good.
Circle. And then I multiplied that by 12.
That's it.
9.519. Be in the fourth quadrant.
So the amount of openness, when you convert, how does the amount of openness change when you convert from one to another? Yeah, the openness is the same, right? We're finding it in a different unit. So you took your percent of the circle. You said was was that 5/2 pi was 0.795, and you took that fraction of 12, and what'd you get? 9.55 marks. Okay, questions on conversions? So you have homework. So I want to talk about homework. So homework, there will be written and web work due Tuesday. Okay, written and web work. Okay, so I want you to go to page 265. In your workbook, 265. Okay, you got a bug 2.6 feet from the center. Oops. .6 feet from the center of the rotation, right? So the radius is 2.6 feet. What's the path of its travel? What kind of arc does it travel on? It's easy. That's a circle, right? If this, as long as the bug stays in the same point on the fan blade, it will travel in a circle, okay? It will travel in a circle. So the radius is 2.6 feet. So for these questions, the bug will start at the 3 o'clock position, and the fan will turn counterclockwise. And you're answering different questions about the radians and the arc length traveled by the bug as it sweeps around the arc counterclockwise. So go ahead and just do that page. You can do that page, and my hope is that you'd be solving these based on your understanding of radians rather than here applying a formula. So try to answer these questions based on what radians mean. Okay, what are radians? So try to reason the answers to these questions rather than relying on a formula. Okay, so the first question was, here the bug starts at the 3 o'clock position, and it's going to travel 5.2 feet up to there. Okay, so that's this. I'll draw it in blue. So that arc length is 5.2 feet, and it asks how many radians. So based on our understanding of radians, how many radians is that? Con? Why? How come? Yeah, why is it 2? What's that? Okay, so and why would you do that? So why is it 2? Brooke, did you get 2? Can you explain why?
Well, the radius
Okay. Okay. So you're using the formula. So who can explain it in terms of what radians mean? Christian,
1 radian is 1 radius length.
right?
The radius right now is at 2.6.
Okay.
2.6 times 2, or 2 radius length is going to equal 5.2.
Right.
It's 2 radius, or 2 radius.
Yeah, so you notice that the distance the bug traveled is twice the radius length. And so that arc length then is twice of the radius length. So the angle that would cut off 2 radius lengths is 2 radians. Because the arc length is twice the radius, so we got an angle that's cutting off 2 radius lengths. That's an angle of 2 radians. Okay? Let's see. Somebody else. Adi, how did part B go? So can you use the same reasoning to do this one? 11.7 feet.
So that's just saying from the 3 o'clock, it went 11.7 feet around the circumference
Okay?
of the imaginary circle. So if you want to figure out how many radians that is, you divide 11.7 by the radius length,
Okay?
which is 2.6, and so you get it's traveled 4.5 radians.
Yeah, so we're going to take the whole arc length, 11.7, and we're going to split it up, break it up into lengths of 2.6. And we're asking how many do we get? How many lengths of 2.6 do we get to make it around 11.7 feet? That's exactly what division does, right? 4.5 radians. Okay, so what we're going to, so that's a little bit, that's kind of review, talking about practicing with radians. So now what we want is to determine, say, the position. So given an angle in radians swept by the bug, we want to determine the location of the bug. Really important. And what do we use to mark off location? So what do we use to mark off location of a point? How can we get location? Alex?
Coordinate points,
Yeah. Okay, so it's like coordinates, okay? So we're gonna use some different terms here. So we're gonna start by talking about a horizontal diameter of our circle. And relative to that horizontal diameter, to get location, one thing we can say is, what's the vertical distance above the horizontal diameter?
Oh, I got it.
So that red line, the horizontal diameter is the blue line. The red line is marking off the vertical distance above the horizontal diameter. So what was the radius again? 2.6 feet, right? So tell me what the vertical distance above the horizontal diameter is now. Isn't it 2.6? All right. Estimate it now. What's the vertical distance now above the horizontal diameter? Just estimate.
Like 1.9, 1.3.
What is it about? 1.3. It's about half, right? So it's 1.3 feet above. What's that?
How can we estimate the distance?
Well, what was my first one I gave you? How many feet was that?
Yeah, that was, it's on a 90 degrees, so it's the
So-
radius basically.
So yes, 2.6 feet. So now I showed you with those lines that it's right about half now. You see? It's halfway up.
Oh, I get it.
So like 1.3. Okay, what about now? What's the vertical distance above the horizontal diameter? So he said negative. Do we have to put negative on it? Yeah, if we're defining as a distance above, then whenever the bug is below, we got to use negative. And he said negative 2.4. What do you think? Something almost negative 2.6, right? Because the minimum would be, the lowest value would be negative 2.6. Okay, so is feet the only way to measure that? Is feet the only way to measure this vertical distance? So we could use feet. So that's what we just practiced, using feet. But what else could we measure the vertical distance in? What's that? Okay, inches, true. Yeah, so we could use some other. Okay, meters, inches, miles, something different than that, though. What's that? Okay, so radians is openness. Radius lengths. Radius lengths. We could measure this vertical distance in radius lengths. And this is going back to the idea, that every circle is like the unit circle. So right now, in radius lengths, what's the vertical distance above the horizontal diameter? In radius lengths. Some people are saying -1. That's right. Do you see that's -1? What about now? What's the vertical distance above the horizontal diameter in radius lengths? About a half, right? It's about half of a radius length. What about now? In radius lengths, what's the vertical distance above the horizontal diameter? Negative. Oops. Maybe negative 0.2. It's less than a quarter even, right? Negative 0.2 radius lengths above. Okay, so this concept of measuring vertical distance, both in feet, in this case feet, and then also in radius lengths, is really important with where we're going. And then we could have the same conversation all over again. How? horizontal distance from the vertical diameter. To the right of the vertical diameter. We do the same thing again. We could say, how far is the bug to the right of the vertical diameter, using feet and using radius lengths. Okay, so there's a few webwork problems where you're going to have to use this idea and approach to answer the questions. Have a good weekend. See you Tuesday.